Welcome to the fifth and final video for the 7th class session of and series of instructional videos. In this video we'll be going over handout number 2 and we'll start out with a little review. We said that for most cases where you have cyclohexane chairs with multiple substituents, the change in free energy between one chair conformation and another is simply additive for those substituents. So from table 4.3 in the Volhart text, you could reasonably calculate the change in free energy for conformation A of this cis 1-fluoro-4-methyl cyclohexane going from conformation A to conformation B of negative 1.45 kcals per mole. For this particular trans 1,3 dimethyl cyclohexane, for conformation C going to conformation D, our change in free energy would be 0 kcals per mole. One can use table 4.3 to get a rough estimate for cyclohexane ring flips with multiple substituents, but the estimate that is in our classical additive way does not take into consideration certain 1,3 diaxial interactions or 1,2 interactions of the substituents. We handled one non-additive case in our 4th lecture video for this 7th class time, and we'll look at another one this time. So in conformation E of this cis 1,2 dimethyl cyclohexane going to conformation F, our delta G is 0 kcals per mole. There are no special 1,2 interactions that are changed net overall. Excuse my spelling of special here. However, when we look at the trans 1,2 dimethyl cyclohexane in conformation G going to chair cyclohexane conformer H, we might calculate a change in free energy of negative 3.4 kcals per mole, so 2 times negative 1.7 kcals per mole. But when we experimentally try to ascertain the change in free energy, what we observe is negative 2.5 kcals per mole. And this is because there is one gauche butane interaction between these methyl groups in conformation H that we form when they go from an anti-gauche an anti-butane conformation, like conformation in conformer G, to this gauche butane in conformation H. So in that process of forming a gauche butane interaction between these two methyl groups, we have to add that in to our negative 3.4. So 0.9 plus negative 3.4 is overall negative 2.5 kcals per mole. So in this handout, we ask you to draw Newman projections for G and H. Instead of drawing them on this handout, I thought I would simply build a model. And so here we can see, conformation H, where our two methyl groups are both equatorial. And if we were to cite down this carbon-carbon bond, what we would see is, lo and behold, these two methyl groups are gauche to each other. So of course, in the former conformation G, they were both axial, these two methyl groups on our chair cyclohexane. And if we were to cite down that bond, we see they're anti with respect to each other. And yes, we're alleviating a set of 1,3 diaxial interactions on the bottom plane of the ring, as well as a set of 1,3 diaxial interactions on the top plane of the ring when we transition to the other chair conformer. But in that process, we also form this gauche interaction. So we have to take that into account. So it's 2 times negative 1.7 plus 0.9 kcals per mole for this gauche interaction that we just formed. I hope that is somewhat clear. On the other side of our handout, just to finish this off, we have a little bit more in terms of naming bicyclic molecules. So I thought it would be useful to introduce you to naming for some molecules that have multiple rings. When your rings are joined by one carbon, a quaternary carbon, we call that a spirocenter. And so there's a systematic way that we can name these. Compound 1, for example, is named Spiro 5.5 in brackets, undecane. Well, how did we come up with that? Well, the answer is, what we do is when we encounter a ring joined by a single carbon, we count the number of carbons on one side of that joining carbon. So 1, 2, 3, 4, 5. And then we count the number of carbons on the other side of that ring. So 1 prime, 2 prime, 3 prime, 4 prime, 5 prime. And so that's where we get Spiro 5.5. And then we count the total number of carbons. Well, 5 carbons on one side, 5 carbons on the other, that's 10. Plus the spirocenter, that's 11. So it's an undecane. So if we did the same thing with compound 2, what do we have? And we have a Spiro 5.4 decane. So we always start with the greater number of carbons. That would be 1, 2, 3, 4, 5 on the left, and then 1 prime, 2 prime, 3 prime, 4 prime on the right. So 5 plus 4 is 9, but then we have to count the spirocenter, so that's 10, so it's a Spiro 5.4 decane. How about 3? 3 looks like a bow tie. In reality, one of these triangles is twisted such that a carbon comes out of the plane and one carbon goes back into the plane. It's a spiromolecule. There are 2 carbons on one side, 2 on the other, so it's a Spiro 2,2, and a total of 5 carbons, so it's a pentane. So I hope this is becoming easier. Let's try compounds 4 and 5. Here we have 1, 2, 3, 4, 5, 6 carbons on the bottom side of our spirocenter. We have 2 carbons on the top side, so this would be a Spiro, and then brackets 6.2, and a total of 9 carbons, so it's a nonane. How about compound 5? Well, we have 1, 2, 3 on one side, 1 prime, 2 prime, 3 prime on the other side. There's a total of 7 carbons, so this would be a Spiro 3.3 heptane. All right, not all bicyclic molecules have spirocenters. Some are joined by bonds that can either contain 0 or multiple carbon groups. This particular molecule we call trans bicyclo 4,3,0 nonane. How do we get that? Well, we have a transfusion, so one hydrogen's got a wedged bond, the other hydrogen has a dash bond. On the right side we have 1, 2, 3, 4 carbons. On the left side we have 3 carbons, and in the bond that creates these 2 rings, how many carbons are between those bridgehead carbons? 0. So that's how we get trans bicyclo 4,3,0 nonane. And this is a more 3-dimensional structure for it. This guy is cis bicyclo 4,3,0 nonane, so now we have a cis fusion, same idea. You know, we have 1, 2, 3, 4 carbons on the right, 1 prime, 2 prime, 3 prime carbons on the left, 0 in that bridgehead. Here we've got a cis bicyclo 3,2,0 heptane. How did we get that? 1, 2, 3 carbons on the left, 1 prime, 2 prime carbons on the right, 0 between the bridging carbons. This guy, however, is different. This is bicyclo 2,2,1 heptane. How did we get that? Well, we've got 2 carbons on the right, 1 prime, 2 prime carbons on the left, and now we have 1 carbon for a bridgehead. And necessarily this really is cis, because our bridging carbon has to be on the same side of the plane formed by the 6-membered ring. And in total there are 7 carbons, so including the bridgehead carbons, so it's a heptane. So how about this one? What would we name this one? This one would be cis what? Well, 1, 2, 3, 4 carbons on the right, 1 prime, 2 prime, 3 prime, 4 prime carbons on the left, 0 in between. So cis bicyclo 4, 4, 0. How many total carbons? Well, 4 plus 4 is 8, plus 0 between the bridging carbons is still 8, plus the 2 bridgehead carbons is 10. So it's a decane. And then, of course, we have over here trans bicyclo 4, 4, 0 decane, which is locked and will not undergo a ring flip. However, the cis version can. So that concludes our video for videos for our 7th lecture. Thank you for bearing with me through this last rather long one.